Today's lecture is very introductory. It's all about motivating the topic, actually understanding what a double integral is, and also just evaluating some basic double integrals. Anybody seen double integrals before? Anyone? Where have you seen them? What about you? Oh, in this course, okay. Okay, stats, all right, good. So some of you are familiar with them. If you don't know anything about them, don't worry. So I plan to cover the first three sort of subtopics today, and then later on we'll move on to the other ones. Okay. So in this section, we are going to look at functions of two variables, their two-dimensional domains, and the process of integration over these two-dimensional domains. I guess the first question is, why would you want to do that? Who cares? Well, we have some understanding that integration of functions of one variable has nice applications. And you would have seen some of those in first year and maybe even at school. And the basic, I guess, application of single integrals, anyone know what it is? What sort of motivates in a physical sense single integrals? Area, right. Area. That's one of the basic applications. Now, for these functions of two variables, our domain is a two-dimensional set. And instead of using integrals to calculate area, we're going to start this lecture by looking at how we can use so-called double integrals to calculate volume. So you're sort of going up one dimension from what you already know. And why would you want to do that? Well, okay, we might want to calculate the volume of some shape, some solid, sorry. But there's tons of other important ideas, and these sort of quantities vary in 2 and 3 dimensions. So you might have a thin plate with a certain density function, and you might want to calculate the volume of the mass of the plate. Well, you can use double integrals to do that. Again, you might have another two-dimensional plate, and you might want to calculate the centre of mass, or the centroid. You can also use double integrals to calculate area, but I'm not going to talk about that today. We'll talk about that later. So basically, today's lecture is all about motivating double integrals through calculating volume. That's all it is. Now, one very important difference between single and double integrals is that the domain, the two-dimensional domain of our function of two variables, plays a huge role. So you may go, oh, I know integration, I can integrate. Yeah, but in this wider setting, it's far more challenging. So don't underestimate it. Okay? So the big question, what is a double integral? Well, a double integral is like most of the integrals you've seen so far, or probably all of them. It's just the limit of a fancy sum. Now, when I say fancy sum, I really should say Riemann sums. And here's a picture of the Ranger uranium mine in Kakadu. You can see they've got these sort of little steps where they've cut into the ground. And with a little bit of stretch of the imagination, you can we'll see that you can really regard the volume of ore being removed as a Riemann sum, with a little bit of license there. Okay. Now for this lecture, our domains or our sets of interest are going to be rectangles. So we've got a function of two variables, and we've got some rectangle of interest. So if we draw the rectangle here in the xy plane, then we can also draw in the surface associated with that function of two variables. And essentially, the problem is we can form a solid that lies above the rectangle but below this sort of curved blue surface. And a fundamental question here is, how do we calculate the volume of the solid that lies above the rectangle but below the surface? So that's a fundamental question that we're going to look at. And I'm going to use double integrals to do it. Okay. Now just bear with me. I'm going to talk a little bit about Riemann sums. Okay, Jim's had enough already. Let's just see how we can approximate the volume. Well, what we're going to do is slice up. So where are we? We are going to slice up this rectangle just by cutting it sort of parallel to the axes. So imagine now this is the rectangle just drawn in the xy plane. You slice it vertically, you slice it horizontally, and you form lots of little sub-rectangles. Now, let's say those sub-rectangles have a width, say delta x and delta y. And I'm just going to make the cut so all the width of the rectangles are all uniform, okay, and the sort of height of them are all uniform as well. What I'm going to do is approximate the volume that lies above each little rectangle and below the part of the surface that lies above that little rectangle. To do that, I'm going to choose a sample point in each rectangle and then set up a Riemann sum. Okay, so I mean, there's a lot of notation here. Don't worry too much about it. Just listen to what I'm saying. Okay, slice up the rectangle so you have equal widths. You don't have to do that. And equal heights, delta x and delta y respectively. And then choose a sample point in each of the rectangles. Now, here's my little sub-rectangle. I've got my sample point. And we basically form here, on that left-hand side in the picture 4b, we form just this sort of rectangular prism, right? Now, what's the area for a rectangular prism? It's just the area of the base times the height. So what's the area of the base? Well, it's a rectangle with one width delta y and one width delta x. So that's the area of the base, delta x times delta y. What's the height? Well, the height is controlled by f. So the height, f, evaluated at our sample point. So to calculate the volume of that little rectangular prism, it's just the area of the base times the height. So and these are all the same. The delta x, you don't need subscripts here because these are all the same. So this, or if we denote delta A by this, then this is just the volume for this particular rectangular prism. Okay? Area of the base times the height. If I wanted to do that for each of my rectangles and form all these prisms, what I would do is just sum up over the i's and j's here. I've got two summing over the i's and the j's, two summation signs. Now that'll give me an approximation to the volume that we want. So the volume of all these little prisms added together will be a reasonable approximation to the area, the volume that we want. So above this and under this. Now, this is a Riemann sum. But remember I said that integrals are limits of fancy sums, limits of Riemann sums. So what we're going to do is make the edges of each rectangle go to 0. And that's just, if that happens, then the number of cuts will go to infinity, big N and big M. So what you do, you take limits as big N and big M go to infinity. And if this limit exists, independently of how we slice up our region, then we say f's integrable on our rectangle R, and we denote that number by this double integral. Okay, well, I guess this notation. So, if you wanted to sort of compare it with what you've got up here, this would sort of go to this. So the delta A becomes dA, and the two summation signs turn into integral signs. Okay. Let me repeat that. If this limit exists, then it's a number, right? And that number is going to give us the volume that we want. In this case, it would be positive if we're working with volume. And we say f's integrable on the rectangle. Okay, but let's actually do something. Let's do an integral and a double integral and work out what's going on. Okay, I do understand that this can be a little bit boring because you don't want to evaluate Riemann sums all day, right? So the following theorem is due to Guido Fubini, Italian mathematician, all-round nice guy. Suppose we have a continuous function on some rectangle. Okay? Some rectangle. Then, when we write down the double integral, or we can calculate this double integral just by evaluating either of these so-called iterated or repeated integrals. Now, I'll do a particular example now and show you how it all works. So here, A, B, and C, and D are just sort of these sort of bounding parallel lines from your rectangle. Let's do an example and see how we actually evaluate this. So let's say, what have I got here? Oh yes, let's do an easy one. Suppose that's my region of integration. So we're restricting the domain of whatever f we're going to come up with to this rectangle. And let's just say this is my f. I'm just choosing this. I'm just sort of manufacturing it so it's a reasonably easy example. Okay, now, Fubini's theorem says that this integral down the bottom, so the integral of f over r, is just these repeated or iterated double integrals. And you can choose whichever one you want. So let me just choose one. I'll choose, what have I chosen here? I'll choose this one. So here, C and D would be 2 and 3, A and B would be 0 and 1, and F would be x squared y. So let's just write that down. Hang on. Oh yeah, I can do that, yep. Now, a very good tip when you're trying to calculate these double integrals is to just draw brackets in. So what I like to do is just work how you always would work with brackets, is do the inside integral first and then work your way to the outside integral. Okay, work on the inside integral first and then work, so you imagine y is a constant, integrate with respect to x, plug in these numbers, you get a function of y. Then move to the outside integral and integrate with respect to y. Okay, let me show you what I mean. So look at the inside integral. I want to integrate here with respect to x and hold everything else fixed. So if I integrate here, I'll get something like this. I'm going to work out the integrand, and then I'll do the integral with respect to y. So if I can pull out this factor of 1/3, no problem. When I plug in x equals 1, I'll get 1 cubed, which will just give me the y, times y here. When I plug in x equals 0, I'll get 0. So I'll get something like this. Okay, so now what do I do? Well, all I'm going to do is integrate with respect to y. Macaulay, quad 1027.
Oh, thanks.
Okay. So these numbers here then just relate to the y. So I can pull out the 1/2. So I'm going to get 1/6. So 9 minus 4. Ah, mamma mia. Okay. Pretty easy, right? Pretty easy. Let's just go through that again. First of all, I was given this, and I could work it out using either of these iterated integrals. I just chose to do it this way. You could choose to do it the other way, and you'd hopefully get the same answer. So notice that x is between 0 and 1. This integral has to connect with this differential. Okay, so these are kind of linked. You couldn't swap them and not swap the differentials. Okay, so I'm going to integrate here, holding y fixed. I get 1/3 x cubed, sub in, x equals 1 and x equals 0. Clean up this and then integrate normally with respect to y. So these kinds of integrals are known as iterated or repeated integrals. Then they're great for day-to-day integration. So let's do, yes?
Does that theorem always hold true? Because
that's an excellent question. Okay, yes, that's an excellent question. The question is, well, this, if you have a continuous function, okay, then yes, and you're integrating over a rectangle, it's always true, okay? If you're integrating over something that's not a rectangle, like a disk or some other two-dimensional set, it's not necessarily true, okay? Let's do something else. Here's another one. Yeah, I think I can squeeze it in here. Now, sometimes you're just given to start off with. Okay, sometimes you're given the iterated integral to start off with. So here we're integrating x cos xy over the rectangle y between 1 and 2 and x between pi on 2 and pi. So again, let's just draw in the brackets. Integrate with respect to y. So what's x cos xy going to go to when you integrate with respect to y, holding all the x's fixed? Sorry, what's it going to be? Sin xy, that's right, because the x's are going to cancel. Bang, bang. Y equals 2. Okay, so now all I need to do is plug in my y values. And I'm going to get something like sine 2x minus sine x dx. Now it's just a single integral. The integrals that we know and love. We can do that easily, hopefully. So you just integrate it like you would when you're at school. No, I'm not going to repeat that. I'll just, by the time you get to the single integral, I'm assuming you can finish it off. Okay? So that's the computation of these integrals. And Fubini's theorem says that if I have a continuous function on a rectangle, then this general double integral is just either one of these iterated or repeated integrals. Doesn't matter which one you choose. Sometimes it's easier to choose one over the other. Okay? And we'll find that out as how to determine that as we go along. Okay. Now, like I said over here, these integrals are known as iterated integrals. So let's discuss a little bit how they naturally arise in, say, the calculation of volume. All right. Okay, I guess I can put this up. Suppose I've got a rectangle here, and I want to use double integrals to calculate the volume that lies above this rectangle and below the plane. So I know it's very hard to see, but here you've got your little rectangle lying in the xy plane. You've got some plane, that's your z equals 4 minus x minus y. Here, that's the bit that lies here. That's the bit that lies above that little rectangle. And you want to calculate the volume that lies above the shaded rectangle down the bottom and below the plane. Now, you may think, well, I could probably use other methods to calculate that. Well, maybe you can. But let's just look at it in a simple way with double integrals. Okay. What we're going to do is use basic first year techniques. At the end of Math 1, 2, 3, 1, or maybe in other subjects, you calculate volume using slicing techniques and single integrals. Okay? So you can think of this blue sort of strip being formed by just slicing the solid parallel to the YZ plane. Now, if I can come up with some way of representing that shaded blue region, the cross-sectional area, then to calculate the volume of this whole thing, all I would do is integrate along the x-axis from x equals 0 to x equals 2. I would integrate that area function. Okay? Now, how do I find the area function? Well, you use another integral. You put them together, you get a double integral. Okay? Now, it's a little bit hard to see, but suppose x is just a fixed number. Imagine x is a constant. Okay? For each x, I can study this little blue region, cross-sectional region, by looking at the following. Okay, I'm just going to draw it in the YZ plane for a second. So YZ. So imagine the x-axis, the positive x-axis is coming out of the screen at you. Now this is just z. Z equals 4 minus c minus y. So think of this as like a level curve where I've just replaced x with a constant. Now, how do I calculate this shaded area, which is just the blue region for each fixed x? Well, I just integrate with respect to y along the interval 0, y equals 0 to y equals 1. Okay? No, I'm just going to put that as an x just to keep it here. So, okay, I've used a single integral to get the cross-sectional area. Okay, you can see how I can get that shaded region, right? Just integrating from y equals 0 to y equals 1, integrating 4 minus x minus y, right? It's just area. So if I take this and this, and I put this into this, then I get this. It's just a double integral, iterated integral. Okay? So that's how these iterated integrals naturally arise when you're looking at volume. Again, to evaluate this, you would just do the inside integral first, integrate with respect to y, hold the x as fixed, and then you'll get some function of x, and then integrate that with respect to x. Okay, so just to reinforce that, here's one that I've created earlier. Function of two variables. In this case, our rectangle is here. Let's do it two ways. Fubini's theorem says I can do this integral two ways. Either this way, and there I would integrate with respect to x first, and then integrate with respect to y, just like we've done. So I get 4. Now, Fubini's theorem says I can reverse the differentials and reverse the integral signs, and I should get the same answer. Let's see. Okay, so I've reversed the integral signs, I've reversed the differentials, integrate with respect to y first, and then, yes, that was lucky. I'm glad that one worked out.